All right, hi there. I'm Gus Burkini, and today we're going to talk about IP equals PSPACE. And I'm really making this video because I tried to learn this topic by myself after taking a complexity course, and my professor showed this result right here. This P sharp P is in IP by showing sharp status in IP. And he said, like it's worth, if you have the time and you're interested in this kind of stuff, to actually sit down and go through the full proof, the TQBF is an IP, that IP is actually equal to P space, not just this P to the sharp P result. And when I tried to do that, I found that a lot of the online resources that I would normally use, uh, like even some of Ryan O'Donnell's lectures, which are really, really good, I recommend looking at regardless. He said the same thing of like, oh, like you should figure this out on your own time. And when I sat down and actually tried to do it, I found it kind of hard to do without as many resources online as I would like. So I'm trying to add this into the world as a as another resource for people who are doing self-study and trying to figure out this result. Um, as I've already mentioned, this lecture is going to be better if you have already seen this initial result, this sharp set as an IP. I don't know if it's strictly necessary, but I don't think I've intended for someone who's taking a complexity course to see this. And if you haven't seen this proof, you can look up, even if you look up IP equals PSPACE and you try to watch most videos for that you'll find online, uh, will actually only show you this sharp set as an IP result and not the TQBF as an IP result, which is really what you need. So let's just go through. Let's start, and we can start by reviewing this sharp set as an IP result. So the kind of steps for this, if you remember, are you take the Boolean formula you get in. That's some Boolean formula, some quantified Boolean formula, and you turn it into a polynomial. And then you sum over all the 0, 1 inputs to that polynomial. So you have all these sums, like, this is over the first variable, over the second variable, and then over the nth variable. And you make the prover tell you the whole sum. So you say, okay, I have this whole sum, and it's equal to some alpha. And then at each step, you kind of peel off these sums, which are equivalent almost to these exist quantifiers, one at a time, reducing to a simpler polynomial. And at each step, you want to maintain this property that if the prover made a correct claim, then they can continue to make correct claims and convince you that it's correct. And if they started with an incorrect claim, right, that this sum was actually wrong, they were lying about this. This is a not equal, not an equal. Um, that they are forced to continue making incorrect claims. And then at the end, once you've peeled off all of these quantifiers, all of these sums, you'll be able to see that the final claim is incorrect, and then you can discount the entire line of reasoning. Okay, so with that, a little more background, we need to talk about what TQBF actually is. It stands for Totally Quantified Boolean Formula. And I find this easiest to understand through looking at the examples. So like SAT, right, you have this like exists x1, exists x2, all the way to exists xn for your n variables, and then some formula. Unsat is the same thing with for all quantifiers instead of exists. And then TQBF is this alternating list of quantifiers. So it's exists x1 such that for all x2, such that exists x1, x3 for all x4, etc., until the last quantifier, which we'll call Qn, right? Q for quantifier. And then some Boolean formula on those n variables. And whereas SAT is NP complete and unsat is co-NP complete, TQBF is PSPACE complete. And the proof for that, I'll leave to you. It's not so bad, and you can look it up also if you need. And so the TQBF problem is this set of true quantified Boolean formulas. And so our first goal, just like above, in SharpSat, when we computed this Boolean formula to a polynomial and we turned it somehow into this sum over the polynomial, is to do the same thing. Turn this TQBF instance into an algebraic expression. So we have a couple things to do here, right? We have to figure out what to do with this. Oops, I've actually made a mistake here. Let me fix this. So we want to arithmetize the formula. Oh, wait. Oh, gosh. Yeah. We want to arithmetize this Boolean formula so that it equals not just a polynomial. In fact, I'm just going to delete this. But what we'll see is it's actually going to be a bunch of operators, one for each quantifier, and then so we'll call this the nth operator on for operator, and then a polynomial. Okay. So our first step is going to be looking at how we create this polynomial. So how do we turn this Boolean formula into a polynomial? Well, it's basically the exact same as you've already seen the sharp set. You take every and clause in your Boolean formula, you turn it into a multiplication, you take knots and you do 1 minus. Then for ors, you can figure out exactly, or you can just use De Morgan's laws, say it's the knot of not x and not y. And what you notice here is that the degree of the original polynomial is going to be less than 3n, because each clause will say has less than 3 variables. It's the same in TQBF. You can do it with 3 variables, and you don't need arbitrarily large clauses. And each or and simply adds the degree of its components, and the knots leave the degree unchanged. This is all the same as is in the P the sharp P proof, the sharp set proof. And a kind of a good thing to notice here is that as long as we're looking at 0, 1 inputs, this polynomial is always going to be equal to the Boolean formula over those same inputs. And this is the property that we really want. And also, this is true over any field. So whatever field we want to look at this polynomial over, this is still true, because at every step of the computation, it's just 0, 1, and the how 0 and 1 behave with each other, how they multiply and how they add, are the same in every field. So that's really good. Is we get to choose basically whatever field we want to operate in, and we're actually not going to worry about what field exactly we choose until the end. To convert, now we look at converting these these quantifiers. So first, let's look at the for all quantifier. We notice that for all xi over some phi of everything and xi and everything else, this is the same as saying phi with xi set to 0 and phi of xi set to 1. And we already know how to do this, how to convert x and y into a polynomial. So we just do the exact same thing here. So for all xi turns into the product over xi in 0, 1 for all of this. And for our convenience, we're just going to write this using this this notation, which is product xi, and we're only going to be doing this product over 0, 1, so it's totally okay. For exists, it's similar. It's unlike in the sharp set, we can't do a straight sum because we're not worried about this, like how many. We're not worried about counting. We're worried about whether it's not or 0. So if we just summed, we would get this issue where the polynomial with xi set to 0 plus the polynomial xi set to 1 could equal 2. So instead, we do the same exact trick we did up here. We do this coproduct, where we do basically 1 minus the product of 1 minus these things. And the symbol we use for this is this coproduct symbol, this upside down pi. So now we have this algebraic equivalent for our TQBF statement, which is this series of operators and then a polynomial. And it's worth just for a moment thinking about what these operators actually do. And what they are is they're maps on polynomials. They take a polynomial and they spit out another polynomial. And in particular, they take a polynomial with n variables and they give you a polynomial with n minus 1 variables. So they reduce the dimensionality of the polynomial. And so the whole expression with our 1, 2, 3, all the way up to n operators in our n-dimensional polynomial is actually like a zero-dimensional polynomial, zero-variable polynomial, which is just a number. And of course, because we're at each step, we're only looking at 0, 1 inputs, and because we've specifically constructed this polynomial so that this is true, the number, right, the number that this polynomial is going to be 0 or 1. Awesome. And we know that we're just trying to figure out whether this TQBF is true or false. And so we know that this is 0 if it's false and 1 if it's true. So that's great news. Another thing to note is that if we knew this polynomial, right, this like what I'm calling P prime here, which is basically this whole expression, except you don't do this final operator. So you just do the operator on x2 all the way to n, but you leave off this first coproduct. So that's what I've written here. We could easily compute this last step just by hand. But actually, we can't really, because the degree of this polynomial is too big. Every time you do an operation on a polynomial, you multiply the degree by 2. And we can see that that's true by looking at this product, right? You're taking two polynomials, multiplying them together, it's going to be the sum, so that's 2 times two polynomials. Same thing here, it's just, there's a little more 1 minuses, but the adding a degree 0 polynomial, which is what 1 is not really, it doesn't change the degree. So every time you multiply 2, so if I do n operations, I have a degree 2 to the n times whatever the original degree of the polynomial, where it's something less than 3m, where m is the number of clauses, polynomial. And so you can't even write down this p prime because it has too many terms. So this is Shamir's big insight, is that to solve this, we need to somehow reduce the degree of the polynomial. And I say this is Shamir's big insight, it's also kind of where the messiness of this whole proof goes in, and why your complexity theory professor probably didn't teach it, because it gets kind of annoying and weedy and kind of weird. So we want to just remember what we want, which is that on 0, 1 inputs, the polynomial is equal to the original Boolean formula. And what we notice is that on 0, 1 inputs, any variable raised to the k is just equal to the variable itself, right? Because 0 times 0 times 0 dot 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 is equal to 0, and 1 times 1 times 1 times 1 dot 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 is equal to 1. So we have this new operator, which takes a polynomial and basically just goes through and looks for every xi, every element xi, so we were writing it like this, and rewrites any of those terms, just deletes the exponent. So xi to the k just becomes xi. And I have this example here where if we're going and looking at x2, we're going to go through all these terms. On this term, we're going to leave the x1 alone. We see the x2, we're just going to get rid of the x4, so that's what we do. Then over here, we're leaving the x1 alone and the x3 alone, as you can see. And then here again, we delete the exponent from the x2. And this operator, at least to me, felt really weird when I first saw it, because it's kind of like, I don't know, it just doesn't feel like a good thing to do. It's like, how would you write that down mathematically? Like, it's like you're doing sort of like a string manipulation or something. These polynomials are not related. It's not a linear, it doesn't satisfy any of our wants for the kind of operators we would typically do on operations you do on a polynomial. But it's definitely an operator. It's well defined. It maps things. It's a function, takes in a polynomial, spits out a polynomial. It's totally fine. And really, all we care about again is that this property that on 0, 1 inputs the polynomial agrees with the Boolean formula. And under this operator, if you take in a polynomial that agrees with the Boolean formula on 0, 1 inputs, then you're going to spit out an operator, a polynomial that has the same property. So now we have this whole, we've basically completed the arithmetization of the process. We have our original polynomial, we have a bunch of degree reduced operators, then we have an operator, a regular operator, a product, or a coproduct, and then more degree reduces, then another operator, and then once you get to the kind of beginning, these operators have removed all the variables, so you can only degree reduce on variables that are still in the polynomial. So we're only reducing on x1 and x2, and only x1 in this final step. Cool. This is exactly what I've said here. So this question, right? Why don't we just degree reduce on everything? It's complexity theory. We don't care about these little efficiencies, and it's because of this thing where if you've already done the coproduct on the ith variable, then you can't degree reduce the ith variable because the ith variable doesn't even exist anymore in this polynomial, basically. So you can't do it. And it's also worth just stepping back and doing a little counting and wondering how many operators are there. And so we can look at this thing. We have n products or coproducts. And then in between each step, we start with 1 degree reduced, then we get 2, and then all the way up to n degree reductions in between the last coproduct and the polynomial itself. So that's obviously O of n squared. This is also O of n squared. So we can say there's roughly n squared operators, which is good. Polynomially many. That's what we want. There's something, if you're looking at other people's work, they might write something like this, and this is kind of a mouthful to get through, but essentially once we get to the protocol, you'll see that we assign constant values to certain variables, and they will write like here the degree reduction on the ith variable, where the first through elf, which includes this ith variable, have been assigned constants. And this doesn't really make any sense because once you've plugged in a constant to the polynomial, like how can you do this process? You can't, because for the exact same reason, we can't just blindly degree reduce on every variable at every step, because the variable doesn't exist anymore in the polynomial, right? We've reduced the dimensionality of the polynomial. Really what they mean by this is you do the degree reduction on this whole polynomial, and then after you do the degree reduction, you plug in this value. And so this is the form that I'm going to write this in because I think it's a closer way of understanding it, and it really emphasizes this fact that the degree reduction is almost like a symbolic operation. It's that you have to do on the polynomial as it exists as a polynomial, not once it's evaluated. Okay, so to remind you, our goal is to figure out whether this whole expression is 0 or 1. And so now we get to the protocol. I'm going to take a glass of water. Okay, so the first step of the protocol is that the prover makes a claim. So either this whole thing, oops, didn't mean to erase, I meant to highlight. Either this whole formula is a 0 or it's a 1, and we're going to call this gamma 0 for whatever their claim is. And then kind of the broad strokes is that at each round, the verifier makes the prover commit to a new claim, and it kind of peels off these things one by one, starting at the beginning. So we have right here, we have this claim starting with the first operator that it's equal to gamma 0. And so you can imagine in general, we're going to have start with the jth operator and end with the kth. And here, I'm kind of abusing notation. This operator could be a coproduct or product or coproduct. It could also be a degree reduction operator. And the verifier is going to kind of force the prover to using this claim to commit to the next claim, starting with the j+1th operator, still going to the kth operator, but with some new gamma. And the crucial thing is that this gamma 0 has to be in 0 or 1, right? This whole statement is either true or false. But these intermediate claims, actually, we can use our whole field. So this gamma j-1, as long as j-1 isn't equal to 0, can be anything in the field. That's kind of how you get your flexibility to determine whether your claim is correct or incorrect. And the goal is that if the prover gives us a correct claim, they can give us another correct claim with 100% probability. And if they start with an incorrect claim, right? So this whole thing is actually equal to 0, but they tell us it's equal to 1 or vice versa. Then they're forced into making another incorrect claim with very high probability. And our hope is that we can get that probability high enough that when we take the union bound over every one of these steps, it's still a high probability that the first incorrect claim leads to a final incorrect claim, and that we can check and verify. Okay, so how do we do this? First, let's just do a little notation. So let's say that xi is the variable associated with the jth operator, because as I was saying, sometimes it's going to be a coproduct, sometimes it's going to be a product, sometimes it's going to be a degree reduction. And then we have these constants W1 through WL in the field. I honestly, maybe in the literature, people actually mean omega by this, but I'm going to call them W because that's kind of how I read them in my brain. And this L here is kind of the number of variables that the polynomial with the jth operator still has left. So at the beginning, this is going to be 0 because we have all of our operators. Each product and coproduct removes a variable, so there are no variables assigned. And as you kind of as this j gets bigger, there are going to be more and more variables left in our final polynomial. The prover then sends a univariate polynomial like p tilde j that they say is equal to this clause, which is O j+1 all the way to OK of p. And actually, I should be a little more precise here, is that it's this whole thing evaluated at W1 all the way through WL, but and actually it's not quite that because wherever the xi is in there, it evaluates the xi instead of whatever value may have already been assigned to that variable in our dimensions. Okay, let me say that all again because I think it was a little jumbled. The prover is going to send this univariate polynomial that they say is equal to all these operators, starting with the j+1th operator, evaluated at this location, which is already these same constants, except for instead of wi, if we've already assigned a constant to wi, we're evaluating at xi. And if we haven't assigned a constant to wi yet, then that means that this jth operator is a product or a coproduct, right? It's removing this wi. So it's going to look the exact same, only xi is going to be right over here at the very end because it's a kind of a new variable. But either way, it's going to be a univariate polynomial. And then the verifier can check this step by performing this jth operator on the univariate polynomial and evaluating it at all these other points. And because this jth operator and asserting that this is actually true, it maintains their previous claim. And here we actually are plugging in, if we've already assigned this wi to, right, if this jth operator is a degree reduction operator, and so the ith variable is still in this polynomial, we assign our constant wi in here. It's all good. And then we either, depending on whether it's degree reduction or a product coproduct, we or just simply assign wi as a random element in our field. And we establish the new claim is essentially that gamma j is equal to the polynomial evaluated at this new wi. And then at the very end, after we've done all this, we check with our original polynomial that their final claim is correct. Okay, that was a real mouthful, and I didn't get into a ton of the details, so we're going to step through what it looks like for a product and what it looks for a degree reduction. And the coproduct case is the exact same as the product case, basically. Okay, so if this jth operator is a product, let's think about what we are looking at. The first thing to look at is, let's say our claim is correct and we have an honest prover. So this is one case. Then this is the kind of situation we're in, where there's a product on xi and then a bunch of operators, and when you evaluate them at the points that we've already assigned randomly, our w1 through wi minus 1, you get our gamma j minus 1. So the honest prover is going to send this exact polynomial, right? It's just this whole thing starting at the j plus 1th operator and evaluated at this point w1 dot 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 wi minus 1 with xi left to vary. And then the verifier does this very simple check, evaluates this polynomial at 0, evaluates it at 1, and asserts that it is equal to gamma j minus 1. And clearly, because we've picked this polynomial this exact way, this is going to be true because the honest prover has sent the polynomial that makes this true. Okay, soundness is a little more complicated, maybe. This is if we start with an incorrect claim and a malicious prover. So the malicious prover is trying to turn this incorrect claim somehow into a correct claim. Our first statement, our previous claim is the same, except this is a not equals because the claim is incorrect, right? If the prover is going to send us some univariate polynomial p tilde j, and the first thing we notice is that if p tilde j is equal to pj, right, like this polynomial that the honest prover would send, then the check immediately fails because pj of 0 times pj of 1 is equal to this whole expression, which we know is not equal to the gamma j minus 1. So this claim is false, and the verifier knows that the claim is false and would reject. So the malicious prover has to send some p tilde j that is not equal to the same polynomial pj that the honest prover would send. And we set this, we remember that our new claim we're saying is that gamma j is set by saying that gamma j is equal to p tilde j at our newly assigned random variable. And the next claim we're making is essentially that, right, it's it's that this whole expression, right, starting with the j+1th operator on our polynomial, is equal to gamma j. So the claim really that they're making is this claim, that the p tilde is equal to p, and in fact these should have little subscripts. Yeah, p tilde j is evaluated at wi is equal to pj evaluated at wi. And so now we can ask ourselves this question, like, how many points are there in the field such that p tilde of wi is equal to p of wi? And the answer is it's almost polynomial identity testing, right? It's checking whether it's the roots of p tilde. Sorry, this is also a little wrong. These are actual variables, not constants. Yeah, so it's the same as the number of roots of this polynomial, p tilde minus p, which is just the degree of p tilde or p, which in this case, because we've done all the degree reduction and it's a univariate polynomial, is actually just 1. So the probability of an incorrect claim going to a correct claim is 1 over the size of the field, which is good. That's a low probability if we choose a big enough field. Awesome. Now we're going to look at soundness and correctness for the degree reduction operations. And so our first case, again, is if we have an honest prover and a correct claim. So if we start here with our degree reduction and all these polynomials, this is kind of the situation we're at. As I said before, we have all our constants, including a constant for the xi that we're looking at right now. And the claim is that it's equal to some element, field element, gamma j minus 1. So the honest prover, as above, just sends this pj polynomial that is exactly equal to this polynomial evaluated at up to the j+1th operator, and with xi in this xi substituted in here instead of wi. The verifier checks that if we reduce the degree of that polynomial and then plug in wi, we get our claim, and everyone's happy. And it's worth actually noting that this polynomial is going to have degree less than or equal to 3m if it's in the first thing before we've done all the degree reductions. And then after that, at every other stage, it has degree at most 2, actually, because we degree reduce between every product or coproduct so that the element going into that is all have degree at most 1, and then the coproduct or proproduct multiplies it by itself, so you get the polynomials will have degree at most 2. Cool. Again, we have to look at the soundness case, which is a little more complex. You have a malicious prover and an incorrect claim. You start with this degree reduction, and this whole statement is not equal to gamma j minus 1. And again, basically, we have the same logic where if the polynomial that the prover sends is equal to the polynomial that the honest prover would send, then the check fails. So they have to send some different check. And as in the previous case, the new claim is exactly equivalent to claiming that this p tilde j is equal to pj. And so the probability of failure here is the degree of pj over the size of the field, and the degree of pj is less than 3m in every case, and it's usually exactly 2, but 3m is good enough for us in complexity theory. So what's the probability in general that a malicious prover can convince us of an incorrect claim? Hopefully you agree right now that an honest prover can convince us of a correct claim with 100% probability by just telling the truth, giving the polynomial we expect to But if a malicious prover starts off with an incorrect claim, what's the probability that over all these operations, at some point they turn into that incorrect claim turns into correct claim, and we don't catch it at the end? Well, we can take this just the union bound on each of these operators. So if we scroll all the way back up and we look at this initial thing, and we're counting how many of them there are, there's, as we said, there's n products or coproducts, and then there's 1 plus 2 plus 3 plus dot 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 plus n degree reductions. So we have less than n squared degree reductions and exactly n products and coproducts. So by the union bound, the probability of failure is less than the sum of the probability of failure at any individual step, which is less than this whole sum, which is equal to this. And so you can see that this R field only needs to be polynomially large. Like, as long as it's to get a probability as small as you want to some constant, it just needs to be some constant multiple of this size. And of course, there's always a prime bigger than that is not like exponentially bigger than that. So you can have a finite field that size, and we're done. So that's basically it for this proof, this IP equals PSPACE proof. As I said at the beginning, I really recommend that you look at a bunch of resources for this. I would say the ones I found most helpful were Alessandro Chiesa has a lecture, and I'll put all these in the video description, I guess. Alessandro Chiesa has a lecture at Berkeley for his probabilistic proofs class that goes through all this in great detail. Ryan O'Donnell, in I think his graduate complexity lectures, not his undergrad, has a great lecture on this, and he's a great guy and probably, just an astounding lecturer. And then there's also some lecture notes. I'm thinking of one from Professor Katz at Rutgers, which I'll also put in the description. I find lecture notes a little harder to read, but once you have figured it out the first time, it's really helpful to have them to go back and remind yourself of little details. Yeah, I hope this is helpful, and happy complexity theory.